Hello, everyone. My name is Peng Wang. It's my great honor to be here at API Days in London. Over the past years, we've all seen how fast the AI workloads are evolving, from retrieval augmented generation to semantic search to document Q&A systems. Today, we are going to talk about building AI-powered application faster and simpler. Many of you have probably tried implementing RAG retrieval augmented generation to combine large language models with your data. It's powerful, but messy. Multiple databases, vector engines, and lots of glue code. What if you could store your data, run semantic search, and build RAG pipelines all in one database? So today, by the end, you will say how to simplify your stack, accelerate development, and build production-ready AI applications without the extra overhead. Let's dive in. So let's start with the challenge we are facing today. According to IDC, over 92% of global data is unstructured. That's exactly the kind of data that drives AI workloads like RAG and semantic search. Executives and IT leaders are also recognizing this shift. 41% say RAG as essential, and over 80% believe Gen AI models using their own data will be a key competitive edge. And this isn't just theory. Cloudware's recent research shows enterprises are moving fast. 2/3 are using enterprise AI infrastructure platforms, and 60% are embedding agent capabilities directly into their core applications. So AI workloads are no longer experimental. They are becoming mainstream, enterprise-critical workloads. And that creates new challenges for platform and database teams, which we will dive into next. If AI workloads are becoming mainstream, the next question is, what does this mean for your technology stack? The reality is, different workloads require different capabilities. For intelligent Q&A chatbots, they need low latency access, semantic search, and context awareness. For log analytics anomaly detection, it needs high ingestion rate, full text search, and metric aggregation. For core business systems, they need strong consistency, ACID, and SQL. And because of this, organizations end up stitching together multiple specialized databases: a transactional database, a vector database, a data warehouse, and even graph on NoSQL database. The result, your technology stack is getting complicated. More databases, more pipelines, and more risk when workloads span across them. From my conversations with many engineers, here is the most they want. For example, one platform for all data workloads, strong consistency and high availability, seamless integration with AI pipelines, elastic scaling on Kubernetes, unified access, and multi-tenancy with resource isolation. But here is the reality they are facing every day. Just like fragmented data systems, trade-off between performance and consistency, complex data movement between services, difficult scaling across stateful workloads, inconsistent query models and APIs, and tenant interference and noisy neighbors. So we use the RAG example to demonstrate how to tackle these challenges. You probably see this in real-world scenarios, such as intelligent search and document Q&A systems. Here is an example of an intelligent Q&A systems. A user is using this application to search for a coffee shop, and he input, please recommend a coffee shop within 500 meters that has an average consumption of less than $8 per person. And the system analyzes the user's natural language input and returns recommended results. 3 kinds of queries are actually required for this natural language input. Filtering within 500 meters is a special query. An average consumption of less than $8 per person is a scalar query. And determine which restaurant is primarily a coffee shop based on its name or type is not easy. So in this case, we need to vectorize the restaurant's features and perform a vector search on the data. In the conventional architecture, the 3 kinds of queries are required 3 different databases to handle. First, the AI application calls an API to search for the restaurants based on the vector database, such as Mavis, Face, and it uses PostgreSQL and MySQL to search for the restaurants within 500 meters and average consumption of less than $8 per person. And then it needs to merge and sort the results returned by the 3 different databases. And this implementation is quite complex and could have potential issues. For example, the vector search could return a large number of records, and filtering these records based on the data returned by the PostgreSQL and MySQL could consume a significant memory and result in performance limitation. To tackle these challenges, we transfer the conventional architecture to a unified architecture with a multi-model database. In a multi-model database, it supports different databases. Support different data types, such as structured data, JSON, GIS, vector, and others. And it also supports multiple index types, such as vector index, spatial index, full text index, and others. It allows you to integrate all your data and perform a hybrid query with a single SQL statement. So for this example, we can transfer this natural language input to a hybrid query SQL. And in this SQL statement, it includes 3 different queries, and we call it a hybrid query SQL. And this were convenient for databases engineers and operators. We'll talk about the practice, and we know why RAG matters. But here is the next question. Do we always need a multi-model database to build one AI application? From the previous part, we know multi-model database supports different data types, such as it supports structured data, such as int, string, and as well as semi-structured data, such as JSON and XML. It also supports KV pairs, spatial data, vector data, and even unstructured data converted from documents, images, and videos. And with this, it allows you an integrated architecture with the unified data access, such as SQL query, NoSQL query, and AI query. And it also has a unified data storage. Let's take a look at the HTTP capability. In the conventional architecture, if a user wants to perform OLAP queries in the database, they need ETL for data synchronization from OLTP database to OLAP database. And this data synchronization could result in data latency and potential risk of data inconsistency. So after that, we transform the conventional architecture to HTTP architecture. And many multimodal databases supply HTTP capabilities, such as CockroachDB, TiDB, and others. And in the HTTP architecture, for customer, no need to use ETL for data synchronization, eliminating the data latency and the potential risk, and achieves true real-time data consistency. Next, let's introduce a new feature of vector search. It's a combination of HASW algorithm and a RapidQ algorithm. Do you know HASW algorithm and RapidQ algorithm? HASW is an algorithm for first similarity search in large datasets, and RapidQ is a technology algorithm to compress vectors. So you can use less memory when still keeping good accuracy. In short, you can think of HASW as how we search efficiently, and RapidQ as how we store efficiently. From our experiments, we combine the HASW algorithm with the RapidQ algorithm, and for the same data size compared to the database with HASW algorithm alone, it needs 1.2 TB memory. But for the combination of HASW algorithm and RapidQ algorithm, it only needs 58 GB memory. It's a 95% memory reduction, and it also has a huge cost saving for customers. Let's wrap up with the few key takeaways. First, simplify. You have OLTP and vector capability in one database with no glue code. And next, faster delivery. You can build RAG pipelines directly with SQL, eliminating the need to juggle multiple systems. And third, more reliable applications. You have consistency and scalability from a distributed database engine. And finally, developer friendly. This database capability can be easily exposed through APIs, like a Q&A and a recommendation service. We are not here to promote one product. We are here to share an architecture idea, unifying OLTP, OLAP, and vector database in vector search capabilities in a multimodal database. You can try it with CockroachDB, TiDB, AringoDB, or other database that involve in this direction. You are welcome to connect me through LinkedIn and my Gmail. If you have any questions, I'm looking forward to your thoughts. Thank you.